I am more than happy to welcome our fourth masterclass today in the context of the SophIA AI Week, and I will elaborate further a little bit in a few seconds. I am Florence Tressol. I have a PhD thesis from University Côte d'Azur, and I am architect within the R&D laboratory in IBM France. And I have the great pleasure and honor to be one of the animators of the data and AI community by Telecom Valley. And this is in that context that I am facilitating these master classes. And first of all, I would like to thank Sandra that is managing more than very well this master classes from a technical standpoint. So thank you so much, Sandra, each and every time for sure.
My pleasure.
So what we have done today, for French people, I mean, we started this earlier this morning at 9 a.m. with the first master class on the usage of geographical data applied to sustainable development by Communauté d'agglomération SophIA Antipolis. Then we moved to another masterclass from a startup, a young company, LCLC, with glasses that are connected through micro machine, I should say, with machine learning inside in order to detect and prevent people to hurt themselves, either while conjuncting or walking. Then we moved with a third masterclass from researchers from Université Côte d'Azur I3S Research Center. The focus has been monitoring cyberbullying through message classification and social networking analysis. And then this is the time for the fourth masterclass by ARM machine learning frameworks and tools. And we would like, with my colleagues of the UX and CX community, to make the link between design and AI. Because guess what? This is SophIA AI Week 2020. And we have launched it yesterday with the World Usability Day. By the way, this is 15 times that my fellows colleague from community UX and CX has organized this World Usability Day. So yesterday. So today, this is the masterclasses day, and tomorrow and 2 days after, we will have the opportunity to follow by the SophIA Summit. And what is the World Usability Day? This is a worldwide event organized each and every year by professionals of user experience with a common goal that is making life easy. And it's all about usage, and it's all about being human-centric when you are thinking about designing a service or a product. And this year, the general theme of the 2020 World Usability Day event is human-centered AI. So it was a great opportunity to link this event in one and common week, the SophIA AI Week. So this event has been organized by the community UX and CX and animated by members of Usage Association. If you did not have a chance to follow it yesterday, feel free to connect you to the Telecom Valley channel on YouTube to have a look to the replay. And before giving the mic to the ARM team, we would like to share with you all what is UX, in fact, what is user experience. We will, when we are designing something, either a product or a service, for sure we are managing a lot of different constraints, and we are merging a lot of different different intelligences and point of view. But and this is maybe what is emerging with the left side end. The road, I mean. But if the usage of the people are not to going to this way, but the other side, you miss the goal of your product or the service, and everybody could miss something. I mean, either the company that is designing the product or the service, and the users themselves for sure. Now, this is why we would like to really try to bridge not the gap, but bridge the link between designers community and developers community, because at the end of the day we are speaking the same language. That means serve the users, and we think that with our complementary capabilities and knowledge, we will be even better to serve men and women that are using product and services. And I'm more than sure that ARM is very how can I say that, willing to do that. This is at least my perception, and I am more than happy now to introduce the fourth masterclass of this SophIA AI Week by ARM, together with Carl, and Mark, all machine learning evangelists. And thank you so much to Remy and Flora to bridge this link and the contact with you, fellow colleague from ARM. So this is your turn, guys, from ARM now.
Thank you so much. Yeah. We're very excited to be here. Or I guess I'm very excited to be here, and I'm excited that you are there watching me here. So yeah, good morning from Seattle, and good evening to everybody there. Mark's actually closer to your time frame, so but we'll get to him next. I will share my screen so you can see what I'm going to be presenting. 1 second. Okay. Can everyone see my screen?
Yes.
Perfect. Thank you so much. Again, thanks everyone for attending. It sounds like you're going to have a great time, and you've already been doing some things. I thank you for that introduction for us. I do think developer experience is often, user experience is often neglected, especially when it comes to machine learning. Just because there's so many different ways things can go poorly or well, depending on what's going on. I will start with a quick agenda for today. I will be going over the ARM ML stack introduction, including a little bit about our hardware, but that'll be brief. I will talk about the ARM machine learning ecosystem and introduce kind of what that means to everyone. Mark is here from ARM Research, and he'll be giving a nice presentation in terms of what we're doing there. And then we'll do a Q&A so that Mark can run away, since technically he's on holiday right now. And so feel free to direct most of your questions to Mark at that time and make him stay as long as possible. We'll take a quick break because I don't think I can sit here for 2.5 hours straight. And then we'll go into the hands-on portion where we will all, or you all will connect to a Jupyter Hub instance I have running on Amazon. And then after that, we'll have another Q&A, and that will be the end of the day. This color is poor. There it goes. Okay. So ARM, if you're not familiar with what ARM does and what it has to do with machine learning, we design IP for chips that then other companies go produce. Most of these chips exist except for the neural processing units that have not come out yet, but have been in the works for many years. They should be coming out in the first batch should be coming out next year early. And the only reason I'm saying all this is to kind of frame what we're talking about today from the sense of hardware. So in machine learning, you do have power requirements, but then you also have specific tasks that you're trying to focus on. And a lot of times when you're deploying these, you want to make sure you have the task in mind from the very beginning, because a lot of times you do not need the biggest, most powerful AI processing unit. All you need is the right tool for the job. And so that's where ARM comes in terms of, we have lots of different kinds of processors, and some of them are the newest batch around the NPUs are going to be focused on machine learning acceleration. However, there has been a lot of work over the last few years to get machine learning done on the CPUs and GPUs that already exist out there in the wild. A better breakdown to kind of see the task to hardware mapping is going to be this. So if this goes from everything from Cortex-M to Cortex-A to our NPUs, which are going to be the ethos line. The Cortex-M are going to be microprocessors. So that's everything from like Arduinos to things like smartwatches or just watches, to IoT devices. So these are very low power, very efficient processors that are meant to run for years with very minimal power, occasionally connecting to the internet if you want or not. Machine learning allows processing at the edge in these cases. They are in use. So biggest use cases right now for Cortex-M in terms of machine learning are going to be vibration detection, sensor fusion, and keyword detection. So for example, on your smartphone or a smart device, keyword detection is most of the time going to be handled by a Cortex-M that's sitting there always listening for that keyword. The reason you do this is because you don't need all the power just to detect a wake word. It's a relatively simple model, so you have a relatively simple low power processor handling that for you. If you ran it on the Cortex-A, which is going to be a bigger processor, more powerful, that of course is going to be a greater power drain. And on a smartphone, people hate that. In low power devices that are out in the edge, or maybe they have intermittent connectivity, or they just have low power. So you can run a Cortex-M on solar with no connectivity, and then maybe it waits for something like a wake word, or visual wake word is something I hear it being called, where it sees a specific type of image and then it can upload to the cloud. So you're able to save more energy by doing this processing locally. That is called, if you're not familiar with it, there's a big movement right now called the TinyML community. Feel free to check that out. ARM is heavily involved just because we're right there and we like supporting it. And it's, I believe the best quote I heard about it is, it's when communication is more expensive than computation. So if you can run that processing locally, sometimes it is cheaper in various ways to do it there. Cortex-A then is going to be larger chips, and this is going to be full operating systems. So Linux, Android, everything now, Microsoft, everything that can run a full operating system, this is going to be Cortex-A. So obviously this is going to be more powerful. It's running in conjunction with many other tasks at the same time. You can also get more power per compute cycle. This also includes Mali GPUs and then the new line of Ethos and NPUs coming out. So here's kind of our broad spectrum of machine learning task paired with a appropriate processor based on the power requirements. I give an overview of that just to make, so here's some of those solutions in terms of how do these actually work in the user's experience, trying to bring it back to that user experience, which is so important. And picking the right kind of tool for the job is very important, because when someone is using your device, you don't need to be using the wrong tool. This is often confusing, a waste of energy. People hate losing their battery, and that's like a fundamental issue of like devices today. So noise reduction, keyword spotting, object detection, and then natural language processing are all very good use cases. And these go from throughout the range of ARM processors. So you cannot interact with hardware without software. That is pretty much proven at this point. ARM has a lot of software. Most of it is often open source, just designed specifically for interacting with our hardware. There's a lot more options I'll cover in a minute, but this is all of the software that ARM owns and supports and controls, open sources, and lets other contributors use and add to. So sometimes a lot of these software stacks are going to be used by our partners for their own hardware and their own optimizations, but the underlying code might be one of these. Today, we're going to be focusing on ARMNN because that's the Cortex-A kind of powerhouse. So this is full operating system. I will not be talking about things like SimSysNN or TensorFlow Lite Micro. That's going to be more on the Cortex-M side. If you can see the mapping down at the bottom here, where the different software stacks interact with the hardware. This is a big graph. We don't need to worry about it. Today, we're focusing on ARMNN. That's the most important part. This is only one side of the software story. Since we do a lot of work with our partners, that kind of makes up the rest of it. And this is always important to understand when interacting with ARM devices, wherever they are. Like, while we do make our own and work on our own software and optimize it, it is open source in most cases, and there are other options that may or may not be using that. Part of that is our ecosystem, and the way we define ecosystem is ARM is in part of it, but together all of our software and hardware partners make this ecosystem stronger through our partner interactions and cooperation. And that's fundamentally how we operate. That's fundamentally how our team operates. Part of that is going to be our AI partner program. So if you or your company is developing some kind of software or hardware using ARM technology, feel free to reach out. I'll share a link later. Right. So that's all I said. This is a snapshot of our ARM AI partner program. I believe it is current. Yes, it is. It is. We have to keep changing it because sometimes our partners get acquired by other companies, and then it kind of shifts things. Babel Labs was one of the most recent ones that got acquired by Cisco. They focused on doing low-powered voice or sound, actually. So this is just a snapshot. The bottom row is going to be the open source frameworks that we work with, which is pretty much all of them at this point. TensorFlow Lite is obviously for microprocessors. PyTorch and TensorFlow are going to be for more larger processors like Cortex-A, and then the Mali GPUs. Onyx is going to be for Cortex-A, and then TVM is, if you're not familiar with it, one of the newest ones. There is the TVM conference coming up in December 2nd, I believe. But that's going to be one of the newest ways to do machine learning for specific hardware. And right now that is Cortex-A and Cortex-M, and then we'll see how the future goes because it's new and our hardware is still not out yet. With that, I'll give it over to Mark because that was the end, and that's the broad introduction. So
Great.
I'll stop sharing my screen.
Thank you, Kyle.
If I can find it. There.
Okay, how's this? Do you see my screen okay?
Yes, we see.
Yes.
Great. Yeah, thanks. So I'm here from ARM's Machine Learning Research Lab. I'm going to spend 20, 30 minutes just giving you an overview of the sort of things that we're thinking about and how this plugs into like the wider picture of ARM and the ARM ecosystem that Carl's been describing. So if we think about the ARM ecosystem, I mean, how many people do we have on the call? I don't know, there's at least an order of magnitude more ARM chips involved in this call than just those people. right? Multiple chips in every laptop, in phones, communication infrastructure between here and there. In fact, there's one of the things we also do is design the world's most popular GPU, despite recent acquisition talks. So in 2018, we shipped something like 23 billion chips. And I say we, I mean we, the ARM ecosystem. And this is very much how we think about it. ARM Research is not a research organization specifically for the ARM company itself, but for our whole ecosystem, providing great tools, ideas, and systems that other people can build on to create great things. And 23 billion chips for a planet of 7.5 billion people, that's a lot. Arguably, ARM plays a defining role in humanity's compute and communication infrastructure. And this is a responsibility that we take very seriously. So in the research group, particularly the machine learning research group, it's our job to look at both compute workloads and compute hardware. And ideally, these two should match as well as possible, because if there's one thing this planet doesn't need, it's going to be 1 trillion devices, all of which are wasting cycles. Now, the biggest shift in compute at the moment, and the most exciting one by far, to my mind at least, is neural networks. And to be a little bit more specific what I'm talking about here, I don't see these as just another popular workload in the way that you may see graphics compute or audio processing as workloads. Rather, neural networks represent a fundamental shift in how we write software. And a part of this is the idea that because neural networks are differentiable, this means that you can solve them with training by example. You can push in a whole load of examples and use very efficient gradient-based solvers to figure out an optimal set of parameters to get the results you want. Now, if you consider a neural network, which is a universal function approximator, right? This is a program by any other name, and it's a program that's learned rather than written. And so from this perspective, the process of training a neural network is really analogous to compiling a program from data into weights or into parameters. And this is very different from what normally happens. Normally, you would sit back and introspect a bit, think about what do I need to accomplish here as a programmer. And neural networks allow us to train that where we have examples, and ideally lots of examples. There's a lot of work in reducing the amount you need, to train either specific parts of this or whole chunks of a pipeline. For example, the live transcription we were looking at earlier, that is working through neural networks, probably end to end from audio processing through to text output. Now, when we come to run a neural network, this set of weights and parameters is treated as a computational graph. This has a lot of benefits over a stream of traditional CPU instructions, for example. One of them is you have a very fixed and predictable runtime. You know in advance exactly how many cycles your neural network will take to compute a single pass, for example. There's no concept of getting caught in infinite loops. This is, at least currently, not a problem at all. And indeed, memory usage is fixed. Typically, you know exactly how much memory usage you're going to use, and you'll use it every single time. It's not possible to have memory leaks. It's not possible to accidentally keep on ballooning the memory requirements beyond what the designers anticipated. And in particular, those memory accesses are very predictable. There's very little conditional computation in current neural networks. So this avoids a lot of branch prediction and these huge multi-level cache architectures that we're so familiar with for human design code. And so this idea of software or parts of software that can be learned, can be trained, this isn't just me or others in ARM talking about in these terms. Andrej Karpathy, if you don't know Andrej Karpathy, he's the director of AI at Tesla. If you're interested, you should follow him and listen very carefully to everything he says. Extremely on the ball. And Pete Warden, likewise, at Google, TensorFlow engineer at Google doesn't begin to accurately sum up Pete's impact on the industry. And they see it this way too. This is a growing realization that differentiable programming, and neural networks are an example of that, is a significant change. One of the most exciting ways, at least from the perspective of usability, is that this kind of software, neural networks, are really, really adaptable. So imagine how much work it would be to take Microsoft PowerPoint as it is today and to optimize it and cut it down so it will run on a microcontroller or a 640K processor. Now, I was brought up believing 640 kilobytes should be enough for anybody. But seriously, that would be hundreds of man years of work, right, for giant, probably C++ or .NET code base. Now, with neural networks, you can take a data center class program, like in this case, I think it's Inception v3, or the speech recognition example we looked at, almost certainly running in the cloud, and do some automated magic, and out pops a new program that's 10 times smaller, and you'll lose a little bit of accuracy perhaps while you do that. If you compress it more, you lose more accuracy, but you have this sliding scale of performance in a way that you just generally don't have with human designed code bases. So this gives us one path to getting really efficient code running on a wide range of different hardware. Now, the techniques that are being used for this today, just walk you through them. Some you'll be familiar with, others you may not be. The first one is just reducing the numerical precision. So instead of using floating point parameters, 32 bits, you can actually use 8 bits, and you can use integer arithmetic instead of floating point. That's much more efficient. You can get like 4x throughput improvement right there, and reduction in memory bandwidth, which is important, and just the size, the overall memory required to store and transmit these networks. An important factor is data reuse. Because most of what neural networks do is multiplying matrices together, you can design them quite carefully to maximize the amount of reuse of data during those matrix multiplies. And in fact, you can go further and compress those weights. So you further reduce both the memory footprint and the amount of bandwidth that you need to get from memory, compute, and put things back. And with bandwidth comes power consumption as well, of course, because memory, particularly SRAM, tends to be fairly power dominant in the system. And finally, because this is all low-level math operations, every now and again a clever technique like Winograd comes up where you can turn an order n cubed matrix multiply operation into order n squared, which can really improve and does improve the performance significantly. And the nice thing about neural networks, again, all of this can be completely transparent to the developer layer, to the person who's designing, training this neural network. They train it, and then all of these techniques are sitting under the hood. And as new one comes out, they just make it better and better without the designer having to change things very much. And this is really important for usability. And finally, I think the area that's had a lot of interest over the last 12 to 18 months is sparsity. This is the idea that typically in neural networks, a lot of the numbers that go into these matrices will be zeros. This may be because the activations crop off at 0, but also you can encourage the network to learn matrices that have zeros in them, to have 0 parameters. In many cases, simply by adding a penalty, a regularization penalty to these weights to say that you're solving this optimization problem, right, to minimize the loss or maximize your accuracy. And you can also add on to that, and let's also have as many zeros as possible in between. And this works really well. And if you know you have a lot of zeros, you can use sparse matrix multiply techniques that either use power gating to reduce your power consumption, because obviously 0 multiplied by anything, you don't need to do that operation. Now, the observant of you will notice that I talked about compressing from 100 megabytes down to 10 megabytes, but this is still a long way from like 640K and below. So if this is what we're doing today, where's the next 10x coming from? And this is the kind of thing that I want to talk about today. So we've been looking a bit about the software tools side of things. Let's see what's going on in hardware. Now, on like general purpose cores and SOCs, here we're talking about things like M-class processors, A-class processors, at least on the smaller scale. These are all gaining sort of wide vector registers. Things like the started coming in years ago with Intel MMX. We have ARM equivalents in the scalar vector extensions. And we're starting to see the introduction of actual matrix multiply operations or instructions appearing in the instruction set. Now, the important things that we need to research here is, okay, setting up these big wide vectors, once you get them filled and executing, that's hugely parallel computation, really reduces your power consumption, improves throughput. But you have to, there's some front-end work that goes into setting that up, right? And constructing your data in the right way. So you want to amortize that setup cost across as many operations as possible. The dot matrix, matrix multiply ops, these are key operations in all neural networks. So anything we can do to accelerate these can really improve the overall use case performance. Now for specific neural network hardware, and I tend to believe that this will be very important going forwards, but that it'll be one of those things that there are some cases where, yes, it's worth going off your main CPU chip to a dedicated accelerator and doing a bunch of stuff and then coming back. But in other cases, because moving data is so time-consuming and expensive, that cursor speed of light, it'll be better just to do a small amount of those directly in the general purpose chip itself. So, but focusing on this NPU block for a moment, there's been a lot of good research on, well, maybe 8 bits is too many. Can we get away with just 4 bits? And some recent research, including from our own lab, is showing you can achieve minimal accuracy loss with as few as 4 bits per operation, which is, again, giving us another potentially factor of 2 improvement. I talked a bit about sparsity, about skipping zeros. If you have hardware support for this, then your hardware can literally just not do those operations or not fetch those zeros from memory. This is both in terms of computing the results, but also fetching the weights from the storage itself. And one of the things we've seen is that many neural networks, once you have sort of these systolic matrix arrays that you get in neural processing units, to do these matrix multiplies, bandwidth is often a bottleneck. So anything we can do to reduce this with compression really helps things. And finally, one of the most interesting areas, and this is looking 10 years out perhaps, is, well, neural networks are very adaptable. They will overcome and continue to function in the presence of quite a lot of noise, especially if you can train with that noise as part of your optimization process. So there's the idea that analog computing may make a comeback. Analog computing can be very power efficient, and the downside is there's more noise involved. But for neural networks, if the noise doesn't matter, that could be very impressive. Equally, I was talking about bandwidth often being a problem. If you can move the compute into the memory cells itself, at least for some parts of the operations, that minimizes data movement once again. And we're starting to see a few commercial products appearing here. There's a very interesting here as well. But for me, one of the most exciting parts of all of this is not the software tooling or the new hardware coming out, but the idea that what if we bring these two together? So this sparse paper was published by our group, I think 2019. And while there are things going on today that I can't talk about yet, I can talk about this paper. So the idea here is that, okay, you have microcontrollers, these are very, very small CPUs. We're talking about tens of kilobytes of memory available, for example. And we want to find ways to fit useful networks like, person detectors. There a person standing in front of this fridge, for example, like visual wake word kind of tasks. How can you fit those down so they'll actually execute on these devices while still giving state-of-the-art accuracy? And what this paper attempted and demonstrated was that you can combine a couple of interesting techniques. The software tooling I was talking about, you can combine that with a technique called neural architecture search. And this, again, is just taking that optimization process that the training of a neural network does and allowing it, at the same time as it's learning what the parameters are, it should learn how many of those parameters should there be in different layers, how should those layers be connected to each other, so that the entire network as a whole is being optimized not just for solving this problem in terms of maximizing the accuracy, but also maximizing its performance on a particular hardware platform. In this case, it has to be few enough parameters to fit down into the memory available, whilst minimizing the latency given these compute characteristics, for example. And this was presented at NeurIPS last year, and you can see in the chart here, this is one of those number of parameters is increasing on the right, and the accuracy on the vertical axis. So you want to be up and to the left here. And these lines here are showing this kind of the way how this paper managed to push that Pareto frontier of performance really quite a long way. This is a log scale here. So an order of magnitude better than previous techniques. And we're going to continue to see a lot of work, a lot of future papers coming out along these lines. So let's a little look at where research has been so far. I'd like to speculate just a little bit, what will all of this look like perhaps in the future? What would if we take this to its logical conclusion, what would the final integration of training neural networks and combining the hardware into that in some way be? And one thing that it might be is, what if instead of compiling the data through the training process down into this graph of matrix multiply operations that we then schedule on some kind of general purpose architecture, what if instead we compiled it directly down into silicon? And last year, my colleagues explored exactly that with a project called Deep Freeze. So the idea here was, at training time, let's say you want to train your mobile net or something on a wide range of images. So you can train that as you normally would. And then you could take the first few layers of that, these shared layers in red, and say, okay, these are going to be the same for a wide range of different networks that I might want to run on my hardware. So in fact, I'm going to compile those directly down into Verilog, into silicon level blocks that will only ever run this one network. So it becomes a fixed function feature extractor. And the weights themselves will be hard coded. Now that gives you some benefits, right? You don't need don't need any DRAM bandwidth or SRAM bandwidth. It can be fully parallel, fully pipelined, very low power, very fast. But it's not at all flexible then, it's fixed. So the top few layers of the network, you could then run on a programmable accelerator and customize them for different tasks. And if this all works well, then you get both higher throughput and lower power compared to doing everything on the programmable accelerator. And this is what the paper shows. By doing this kind of thing, they got over 11 teraops per watt, which is a huge amount of performance with very little accuracy loss. Twice as good as a kind of standard open source accelerator would give you. Now, this is really only the beginning. There's a lot more that could go on here. And yet, I think there's another ARM project that's also coming out of our research called the Plastic Armpit project, which was looking at what if you could print CPU designs directly onto plastic. And then that plastic can be used, recycled, just like normal. In that case, for these kind of single use, like specific use sensors that you might have, like is this packaging of food going off? Is this medicine still good? Has it been in correct temperature and conditions this vaccine bottle the entire time through its transport link and so on. That you could do all of that with just printing this as part of the production process. Now, for things like that, where you have a single device that's only ever going to do one thing, and needs to be extremely low power, power it can harvest from the environment ideally, that's the sort of area where this kind of compiling a neural network directly down into that hardware design could be very valuable. Now, this is just one of the areas we've looked at over the last few years. We've got a wide range of publications, and one of the nice things is that because we're not part of a big sort of closed source conglomerate, but ARM is, and particularly ARM research, is looking to support the ecosystem as a whole. It means a lot of the research we can do out in the open. We can publish papers, produce open source projects, so that our partners can build on it and create great hardware for people to use. And we have quite a wide range of papers from a number of top conferences that I'm not going to go into here, but if you get the presentation afterwards, all of the links you'll find in the presenter notes here. That was a very brief whirlwind tour of what our research is looking at, thinking about when it comes to both training and deploying, especially optimally deploying these neural networks onto what I believe will be Earth's compute and communications infrastructure. Thank you very much. So, Carla, I believe on the schedule, do we have a time for some questions and answers here before we hit the break?
Yeah, exactly. That's what I was hoping for. Yeah, so now is a great time for questions.
Are people asking questions through chat here? Oh wait, we've got a QA tab, that's great. Great, well, I'll just take these from the top and bounce them over to you, Carl, if appropriate. Does that sound good?
Yeah, sounds great.
All right. So top question, if I'm a data scientist with a limited hardware understanding, are there simple ways to ensure my model will work on different edge devices, using a sparse project maybe? Yes. So I think the answer to this is today, no. Today, there's not a simple way to ensure it will work on a wide range of edge devices, and it should be. There should be a simple way. So this is something that a lot of people in, especially the machine learning group that Carl's part of, and some people in research have been looking at as well. So the sparse projects, there's internal tools we're building off of that we hope to be able to show to people in the not too distant future that would make this simpler. There's a lot of other tooling already available from ARM, like ARMNN is a good example of how this is going, right? So ARMNN is a single framework with a simple API. You can say, load my Tensorflow Lite neural network, and then run it. And whether it's running on a CPU or a GPU or an NPU, it doesn't matter to you, the developer, anymore. So there's also a bunch of work going into just adding things into open source projects. So there's a good sized team contributing directly into TensorFlow, looking at contributing into PyTorch, so that if you're using these projects, that things will work out of the box on your various different ARM processors already. So yeah, I think, are there simple ways? Honestly, not right at the moment, although the cases that work with ARMNN will work very well with it. And that's one of the places that's going very well. Also, if you're looking at M-class devices, look at TensorFlow Lite for microcontrollers. This is also your simplest path to getting one thing that just works in a wide range of different places today. And yeah, watch this space because this is a very important area. Okay, if I am an embedded developer, I want to add ML to my IoT device. What help can I get from ARM for this? Carl, do you want to take this one?
Yeah, I can take that. So there's a few ways to do it. Like Mark said, TensorFlow Lite Micro is going to be your best way to do it. TensorFlow in general right now is probably the most supported thing, just in terms of across the ARM stack. So I'd look at TensorFlow Lite Micro. If you're more comfortable with embedded programming, we have a lot of partners that are focusing on making the deep learning side easier and kind of obfuscated for you. Some of those are going to be Keekso. Edge Impulse is really good. They're relatively new. And that's a free tool. They have a free version of their tool. So I would probably check that one out because they're kind of aimed at embedded developers wanting to transition over to add machine learning tools to their stack, if that helps.
All right. Are there any techniques that can help preserve data privacy? It's my favorite question because this is something I'm working on. So yes, yes, there are a lot. I think I'm going to interpret this question a little bit in that you're asking, actually this links into another question that's just come in. Can we do training at the edge and for which class of problems? So yeah, I think the biggest data privacy question, sorry, do you want to say something, Carl?
Dans la conf ARM.
Okay, so I think the biggest data privacy issue is when you're collecting data for training on, right? So if you're collecting data into a data set and a human is going through it and saying, oh yeah, his head was looking left and his head was looking right, there's no data privacy there. So can we do training at the edge on your own device, controlled only by you, that's never sent off your device? And can that enable privacy? And how can we guarantee privacy in those cases? And there's a lot of research into this around federated learning and differential privacy. This is something we're looking at many, many levels of ARM, both on the AI ethics committee is looking at this, research looking at it. And one of the things that we're also looking at is, okay, well, when I have neural networks running on my device, how can I guarantee that this AI camera, for example, that is only supposed to be checking whether my parent has fallen over and hurt themselves, how can I be sure that it will only ever do that, that it's not storing that data or using it for other purposes? And ARM already has some technologies around this kind of data processing called Trust Zone. This is used for things like processing biometric data in fingerprint scanners, for example, where you can be sure that none of the data from this sensor can be processed by anything else on the system other than some signed, verified software. So there's lots of interesting work to be done around that. Can training be done at the edge? Just to come back to that, yes, it absolutely can be. There's some challenges around that. There's a lot of the future improvements we're going to see from this come around two areas called self-supervised learning and semi-supervised learning. They let you use a large amount of unlabeled data, which is what you have at the edge. You don't have labels, but you have data, experience. And you can learn from experience and then just use a few labels that are being collected with an opt-in data center policy, for example. Two questions about spiking neural networks. Do we consider them? Do they help for certain tasks? So I think spiking neural networks are really interesting. I think they're in some ways more biologically plausible than the networks that we have, neural networks that we have today. But personally, I believe that there's enough momentum around traditional quote-unquote neural networks that spiking neural networks are going to be the Betamax, right, of technologies here. Would they have been better? Would they have worked in some circumstances? Maybe, but we're at the stage now where people are designing and producing silicon optimized specifically for the kinds of traditional neural networks based on matrix multipliers that give you orders of magnitude better performance and power. And spiking neural networks don't have that critical mass to get hardware built around them. So I think even though in some circumstances they can be better, they can't compete with the combined, like both machine learning research that goes into traditional neural networks and also not into the hardware research and the ecosystem momentum around that. So I think they're intellectually interesting, but for deployment, I wouldn't really consider them. It'd have to be a very, very strong use case for me to think that they'd be more valuable. Yeah. Okay, more questions. Can we share the slides, please? Carl, do you know if we can share the slides?
I don't know how to do that. I'm assuming we can somehow, but we can find out. Yeah.
We definitely like to share the slides. It can't be that hard. We're living in 2020. We must be able to do this.
Yeah.
I guess I'm going to drop off for the end. Carl, will you take an action just to follow up with somebody at the end about how we can get the slides out?
Yes. I will follow up and hopefully figure that out, but we should be able to do that.
Great.
Yes.
All right. Final question, neuromorphic computing. Is this something I was doing? So I understand neuromorphic to mean computing that tries to more accurately mimic what the brain does or what biology does. I think spiking networks is going a little bit in that direction. This is something I was doing. We definitely have people within research who are tracking this topic actively. But as I said before, I think we have astonishing results from the neural networks as they are, for better or worse. And they have enough momentum in software and hardware that this will be the future for the next 10, 15, 20 years easily. But yeah, there are definitely biologically inspired techniques that are very interesting, and we continue to look at, because we're solving problems that nature's already solved. So we can learn a lot by studying nature itself. All right, great. Well, no more questions on the board. Then should we, oh, what is the state of federated learning? New question, just come in. All right, what is the state of federated learning? Federated learning is in use today, probably on your mobile phone already. So the Google keyboard on Android, the Gboard or whatever they call it, they use federated learning as follows, as I understand it, that the words that you type during the day are recorded only on your device, and at night, while your phone is plugged in, it's already charged, it's connected to power, it's connected to wireless, then sometimes it will be selected to take part in a federated learning process that uses differential privacy so that your word lists are not actually shared with anybody else. But to allow Google and Android as a whole to learn better what kind of words people are using and which ones follow the other ones for their predictive technologies. So I think federated learning is fairly well understood. It's been well studied, lots of papers, it works. The thing that's been holding it back is, as I say, currently you need labeled data, and it needs to be high quality labeled data. So for some use cases, you can get that from a device, right? The user will correct a word if it's wrong, generally. But for other things like face recognition or resolution supersampling and so on, it is not so easy to get good labels from your data. And this is where we're going to see a lot more, a much wider use of federated learning as these problems are addressed in the future. I think 12, 24 months, we'll see a lot more training on devices than we do today. Do we have a team working on it in SophIA? Carl, do you know the answer to that?
I do not know. We have a lot of people everywhere, and I'm not sure where they are.
Yeah, ARM has people in many, many different places. Does ARM have an office in SophIA? It might do. But certainly there's not an ARM research office in SophIA as far as I'm aware. On the other hand, I myself work from home in Germany, where there also isn't a research office, but there is me, so I'm the research office in Germany. ARM's spread across all of the continents, many, many countries. So we do a lot of work online and global collaboration anyway. But no, I don't think there's a team working on machine learning in SophIA. Okay, no more questions yet. We can have more questions. As Carl said, there'll be another QA session after the break, at the end of the session. And you're going to do some hands-on stuff after the break, right, Carl?
Yep, that's absolutely right.
Jupyter Notebooks in the cloud is going to be great.
Yep.
Cool. Well, I'm going to head off back to my holiday. I think if there are any more questions for me, grab people's emails or something, I'll follow up offline like that. That'd be great.
Yeah, I can do that. Feel free to direct more Mark questions to me after this. And thanks again, Mark. That was really good. I always like presentations from research.
This is fun. Okay, great. So 15-minute break, meet back at 10:06. 10:06 European time. So 15 minutes time. Okay,
perfect.
Great. Thanks. Goodbye, everybody.
Feel free to ask questions while I'm going or into the Q&A. We have plenty of time for this portion, but hopefully, feel free to save them until the hands-on portion, just because that's going to be more interesting, and the faster we get there, the more interesting it'll be for everybody. Okay, so Armanin and Darwin AI. This section I'm going to go quickly over. This was done by one of our partners, DarwinAI. They made an open source COVID-19 framework. If anyone doesn't know, there is a worldwide pandemic happening right now, hence Zoom. I believe this was taken a few months ago from the Johns Hopkins COVID-19 dashboard, just showing the spread of infection. DarwinAI is one of our partners. They do a lot of work around custom data sets, and they also have specific techniques around explainability inside machine learning models. They have a platform you can use that uses this and gives you back the information. So if you're looking for a new tool, DarwinAI is very good. And so this is one of the things they did as part of an open source project. They built this model relatively early during the pandemic and then released it as an open source. So that's what we'll be doing today. We'll be using this model, showing how to run it on Armanin, and that's it. I will go over these briefly just because I don't know a lot about the ins and outs of this model because it was developed by them. I'll send you a link though for more information. Yet just yesterday, they did announce a partnership with Red Hat where they're to be deploying this in hospitals in Boston. Anyway, COVID-19 screening is paramount. Making this as quickly as possible, done as quickly as possible and as accurately as possible is incredibly important to containing the spread. Antibody testing is the current one, but apparently it is variable in terms of results, especially around sensitivity and specificity. Chest radiography is going to be one of the more accurate ways to test, but it's also going to take more time because it requires an X-ray. It's not going to be a drive-through thing. You're going to have to go and get a chest X-ray. And then it also has to be looked at by an expert to determine what's going on. Hence, the COVIDNet is what it is called. So this is going to be the machine learning model we'll be doing a little bit with today, just by running it and seeing it in action. It'll give us a good hands-on use case for ArmNN, which I'll talk about in a minute. And this was a joint initiative between the VIP lab in Waterloo, Canada, and then DarwinAI. So it took only a few months, mostly through the helps of DarwinAI's tools. It helped quickly, and they focus on explainability. So if you're interested in that, please check out DarwinAI. Very good partner. They do a lot of good work. And then these are the key steps. The key elements of DarwinAI's tool is going to be the design, prototyping, the exploration, and the audit, where you can see how accurate the model is. You get a lot of explainability results, and then you can quickly iterate without even deploying it. So very good tool if you're interested in learning something new. For more details on this, check out DarwinAI's website, and I can copy these into the chat real quick. This was an article that just came out yesterday while I was looking at it. Apparently they partnered with Red Hat, like I was saying, to get this deployed in hospitals in Boston to start using this as a rapid testing solution. This talk we did a few weeks ago at the ARM Developer Summit. And DarwinAI came and helped us give that. If you want to see more details about their portion of the presentation, plus the work we're about to do, which you probably don't need to go back and see, feel free to check that out. And then also there's a lot more, if you are interested in more videos around learning how to use ARM tools, we do have a YouTube developer channel. Okay, back to the presentation. ArmNN. So ArmNN, I briefly mentioned before, it is going to be one of our software stacks and focus on Cortex-A devices. So here's the quick steps we're about to go through right before the hands-on portion. For a longer talk on ArmNN, there's another video you can go see. This video is also already on that software developer channel. These are the engineers who work on it, so it's going to be a little bit more detailed, a little bit more of a deep dive. a lot of the content's the same, and all of this is obviously online. Okay, so Armanin is one of the main inference libraries for machine learning on ARM Cortex-A processors. Let me fix that slide. It was not super helpful. Okay. This is a quick overview of how it interfaces with the hardware. Generally, you're going to be running it. In most cases, if you're running Android, you're going to be running through the Android NN layer. So you're not going to even be aware of ArmNN, but that is one of the paths to actually use it. ArmNN sits on top of the compute library. There's also an ethos-n driver for the future NPUs that are coming out, but we don't need to worry about that today because they don't physically exist. Today we'll be focusing on the Cortex-A side. And just because that's what we're using. So quick bit about the hardware we're using. We're running a Graviton instance in AWS. So that's why we'll be using the Cortex-A accelerator library for this. Basically, you have your hardware, the compute library. ArmNN is an extraction layer that helps you make it a little bit easier in terms of your traditional machine, like your machine learning and application workflows. Compute library is a little bit expansive. And then there's also a lot more higher level libraries on top of that. ArmNN is open source. If you're interested in contributing, you can do that. It's right now MIT licensed, but it'll be switching over hopefully soon to an Apache 2. It just makes it a little bit easier to contribute. So the Armament components, there's the core, which is the graph builder. And this is literally just the part that takes the model and interprets it, the optimizer, and then the runtime. Parsers are going to be for whatever kind of framework you're using to import into ArmNN. So that's Tensorflow Lite, ONNX, PyTorch via ONNX, TensorFlow, and Cafe, even though Cafe is not super supported, but it's still there. So if you have an older model, it's in Cafe, you really like it, want to still use it, still works with ArmNN. Then there's also the Android NN API. So if you're running on top of, if you're building an Android application, if you use the Android NN API as well as the HAL driver, then you're effectively running ArmNN. So the flows. So in order to use the interfaces directly, you're going to describe a layer, optimize it, add a layer, connect it, and then re-optimize it. And that's effectively how you're going to be running it and what the library does for you. So you load the network and then you execute the inference. You create an ArmNN runtime. You set the options on it, such as preferred backends. Today we'll be using the CPU backend. So keep that in mind. We don't have a Mali GPU sitting there. We don't have anything else. It's just the CPU today. You load the optimized network. So COVIDNet is, I believe, a TensorFlow network. And then construct the input and the output tensors, and then you run the inference. So ArmNN handles everything else for you. You just kind of need to build that funnel into your application. There are a few parsers. These are going to be the way to integrate with common machine learning frameworks, as I said before. Once you construct the parser, it can now be optimized for the hardware you're running on. ArmNN handles that portion for you. You just need to specify what hardware you have. And then there's execute. There's a test tool called execute network, which loads and executes the models. As I said, ArmNN has a driver for the Android Neural Networks API. This is mostly just because one of the most common places you find a Cortex-A is going to be in Android devices. So it makes sense to integrate with that, the native development library for Android devices. Backends. So the backends are going to be focused on which hardware you're running on. Today we're focusing on CPU. So there's also custom backends. So if you're running a different kind of hardware that may or may not be explicitly supported, you can build a custom backend. There's instruction for this on the GitHub page. If you're interested in that, that's going to be the best source. I haven't done that yet. So PyArmNN is going to be what we're using today. This is done because a lot of data scientists and machine learning developers are more familiar with Python. I definitely prefer Python. ArmaNN is natively run in C++. So PyArmNN is effectively a wrapper for the ArmaNN libraries and allows you to run it in Python, which I prefer. So this is built around the public headers for ArmaNN. All operations are delegated, and then it's effectively just a wrapper. You can also download it right now on GitHub. We do have a new upcoming release coming out soon, which will make installation much easier. If you want more information, again, go to the GitHub, and there's also a lot of examples for other things that you can do. We have one other example right now. If we, for some reason, finish the COVIDNet things early, you can try to play with. Right now, that example is not working, but you can also go to the GitHub and run those examples on the AWS instance we have set up. So effectively, the release coming up in the next few weeks, it's mostly around usability. There will be a Debian package. So this works with any, right now, the biggest one it's going to be working with is Raspberry Pi 4 and Odroid N2. Odroid N2 we selected just because it's one of the most common single board computers that also has a Mali GPU next to it. So you can also run acceleration through there. There's a TensorFlow Lite delegate that is coming out, so that'll make it easier just to run through TensorFlow Lite. It'll be another step away from the interpretation layer. And then updating website and documentation to support all this. So more examples, more specific use cases. Keep an eye out for all those things, and those will be posted on our developer website as well as the GitHub. Okay, now it's time for the hands-on section. Hopefully everybody's ready, and I will close my presentation. Okay, now if you can connect to okay, so if you connect to this website right here, I will copy and paste it. I should, if you were registered as of yesterday, I should have your name as a registered user. And I'm going to keep this up. And then, okay, and then this is going to be the part where if you run into a problem connecting, let me know. I will share my full screen just to show you what you should be looking at. If for some reason your name isn't on, okay, connection instructions are going to be first name, all in lowercase, no accents. Apparently that's a problem in Jupyter Hub that I didn't know about. It doesn't allow accents in the username. So sorry, everyone who has a French name. No spaces, no hyphens. For example, Jean-Christophe, there's a hyphen in your name, not a space. And then there were 2 Fredericks and Christophs registered. So just add the first initial of your last name to your user account. And if you can't, just in case you can't read this, this is the website. If everybody can let me know, feel free to unmute, raise your hand, let me know when you've connected. And if you can't connect, let me know and I can figure it out. Oh, and the password is ArmaNN. The website address is that IP address that I just shared, Remy. It's this. This is the web address. And then everybody let me know when you are connected. You should see, okay, done, cool, awesome, Archaea. When you first go to the website, you should see this. Just enter your first name And then the password is ARMNN. Okay. We're connected. Cool. Everybody let me know when you're, uh-oh. Okay, good. It'd be bad if I couldn't connect. Yeah, so everybody connect. If for some reason you can't connect, send me a message, chat me, just send a message in chat, and then we can figure it out. Everybody, once you connect, go ahead and open up there is a README file, a README PDF. Go ahead and open that. That's going to be the instructions for what we're doing today. Go ahead and start reading that. It goes into the details in terms of what the model properties are, how to import it into PyArmNN, and then how to run the application. And you should see, once you open this, follow the instructions, open the inference ArmaNN IPython notebook, sorry, Jupyter Notebook, and that will be mostly done. You can read the instructions and follow along. Let us know if you have any questions. If you run into a problem, let us know. And then, yeah. So far, is everybody connected? Is anybody not connected and having issues? If you are new, if you weren't registered tomorrow or the day before, your name might not be in the username list, and let me know and I can add you or give you a different name, just because there's only 10 or 13 of you. Okay, connected. Cool. Bernard is connected. Is anybody not connected? Is anybody not familiar with Jupyter Notebooks? Would it be helpful if I go through a little bit of Jupyter Notebooks? Remy, okay, yes it would. Okay, Jupyter Notebooks, this is cool. I'll give a quick brief. If you are familiar with Jupyter Notebooks, feel free to start working through that PDF. If you're not, PDF will be there. Don't worry about it. So if you're not familiar with Jupyter Notebooks, this is Jupyter Lab, which is effectively a nicer user experience front end for Jupyter Notebooks. And everyone can see my screen in front of me, right? The Jupyter Notebook. Yes, yes. I'm assuming yes. I can also. Okay, cool. Okay, so in front of you have a Jupyter. This is Jupyter Lab. It's the Jupyter Notebook is going to be on the right side. In Jupyter Lab, you have this extra box on the left, which is going to be your file explorer. There's going to be kernel sessions, which you can see. Effectively, a kernel session is going to be an interpreter for whatever the Python notebook in front of you is doing. It helps to have only one of these running at a time, most of the time, unless you need two. We shouldn't have an issue today. Just because there's so few of you. This is a fairly big instance. And again, as I said, this is a Graviton instance running in AWS. So these are all ARM CPUs that we're running on today. I think it's 64 cores, so it's fairly fast and we shouldn't have any problems today. Anyway, again, kernel sessions on the left. You don't need to know about this for most things. Extension manager, this is all Jupyter Lab things. Settings, extensions, which are sometimes fun and interesting, and then open tabs, which is obviously here. The file browsers, where you're going to be most of your work. If you hit the plus sign, you can do things like a new terminal session or a new notebook. And then you can also upload files here and refresh the file list. This is all effectively just running on your Linux directory. Jupyter Notebook. So this is the one we'll be working with today. It is not fully complete. So what you're going to want to do is read through the PDF file, find the answers that are written there like it's a guide, and then add the answers into this Jupyter Notebook. In Jupyter Notebooks, the main portion is going to be a cell, which are represented by these boxes. You can add new cells with the plus. You can do things like code, Markdown, or raw text. Markdown is just text. So if you type in, my Markdown is very rusty, but you can type in Markdown or just text. So Markdown lets you have like larger letters, add images. With Jupyter Notebook, there's a lot of other extensions so you can view your visualizations easier. I use this a lot when I'm prototyping, mostly because I can run code next to an image, next to more code, next to an image. And that's the great thing about it. To run a cell, you just click on it and hit this play button. And that puts out the output. Oh, I put this. This is the wrong thing. This is where you want to be. You shouldn't get that error. If you run into any errors, double check it, make sure everything's entered correctly. This one. Okay. This is the one you should see. Sorry, that was an earlier one. This is Markdown. These are the cells. You should be able to run the cell, see what version of PyArmNN you're running, which is I think the most up-to-date one. Load image to find the model. And then, so if you have a none type, attribute with shape, you should look in the PDF. And effectively work here, run each cell. It's basically you're stepping through each line in your Python code, block by block by block. And then all the details for filling out these blank things, like here, the parser we need to define, the network we need to load. You can find all that information in the PDF. And then everyone, let me know if you have any questions. Wei is also here to help. Feel free to chat any of us or answer to the group, ask to the group. We will answer those questions. And that's it. Is everyone doing fine? Doing good? I'm really... Yeah, no worries. Yeah, feel free to just read through the PDF is going to be the best thing, Remy, and that will kind of step you through the details. And then just consider Jupyter Notebooks just an IDE. It's just more like each little block it's very sequential. You run it, and then you run the one below it. And imagine you have a lot of stop. Imagine this is one Python application, and you just have multiple stop points between all the little cells in the Jupyter Notebook. So you do it at a time, and you can rerun, you can change it and rerun something. So if I say, like here, I can change it to say, you run it, execute sequentially. It's effectively it. How's everyone else doing? Good? When everyone gets to the point where you run your network, you should get a time printout for the Tensorflow Lite version of the interpreter and then the Armanin version of the interpreter. Feel free to chat us or unmute and say your inference times for each. You should see a difference between the Tensorflow Lite interpreter and the Armanin one. And yes, you should be detecting COVID on this image. This image, feel free to switch out. They're in the assets folder. Oh, I have the older version. You should have multiple images, and you can swap out which ones you're running. No, that was the wrong thing. Yeah, cool. Okay, how is everyone doing? Any issues? Any questions on what we're doing? If you haven't yet, I will step you through the final version. The difference is going to be where the images, the filled out for the TensorFlow Lite file for the model detection. Should have the differences here. Okay. So I'm going to walk everybody through this just in case anybody else is having difficulties. Has everybody run through this without issue? Any questions? Okay. We're using the TensorFlow Lite parser, obviously, because the model is a TensorFlow Lite file. And then we just add the model file to it and defining it up there. Output input binding info. So you need to define basically what's the input for this model with it for ARMNN. Define that. Actually, I'm going to, is this done? Yeah. Okay, run through this again so we don't see the end. Okay, import, load the image and file. Okay, define the inputs, create the runtime, and then define the backend, which are running on the CPU. And those options are going to be defined up here. Here's the preferred backend for this model. And we're going to be running the CPU one. Then you load the optimized network. So basically run it through the optimizer for your hardware, which we just did. Output bounding, and you want to make the output tensor so it understands what the output's going to be. That looks good. You can enable profiling if you want. Feel free to uncomment this out. Sure, why not? And then you run the inference. And you should have a time, elapsed time. And this was with the inference results with PyArmNN. And then you can also run the TensorFlow version down below. So you can run the TensorFlow Lite interpreter. So let's just see how TensorFlow Lite compares. And it should be, the whole idea is that TensorFlow Lite is not bad, but since Armanin is built to run on the specific hardware, it should be a little bit faster. Interpreter, allocate tensors, and you start a timer and run the inference. And the time is 627 milliseconds versus 414. And then this is just the outputs from the model, where it shows the probabilities for COVID-19, pneumonia, or a normal lung. And in this one, it is COVID-19. So any questions? Has everybody finished running through this notebook? Are there any questions about ARMNN as well? And feel free to unmute. Any questions? How's everybody? So if you want to keep, if there are no questions, and if you want to keep playing with Armanin and try some other exercises, there are two options. One, in your COVID, if you go back to your main directory, you should see a bounding box folder. This is one I was working on over the weekend, and it's taken from a Python script. The Jupyter Notebook is not finished, so you could try that. It's basically a work in progress Jupyter Notebook. The other option is if you go into your COVID-net folder. I don't see it on my account, but you should see on my Jupyter Hub account. You should see a fire detection folder. In the fire detection folder, there is a fire detection IPython notebook. You can open up that IPython notebook and run through that one. And this is a model that was done by Wei, and a notebook that was done by Wei, I should say. And the model was from, I believe, from PyImageSearch, which is a really good resource if you're looking at learning to use Python for computer vision. Anyway, so go ahead and you can go into that Python notebook and you can see Armanin running for fire detection effectively. Imagine you have a smart camera, and instead of detecting smoke, it detects fire. So you can have as a smoke detector. I believe the example was described as mounting this to a drone or running it while a drone is flying around and detecting fire in order to fight a forest fire, for example, that were happening over the summer. Are there any questions about Armanin, about this notebook? If I can't answer many questions about the COVID-net itself or DarwinAI, feel free to reach out to them. If you're interested in getting in contact or you need, you are looking for a new tool to use, feel free to send me your information. I'll put my email in here. You can also send me any kind of questions you have around Armanin or developing machine learning models for ARM devices. This AWS instance I will leave up for the next few hours. Next hour, I'll shut it down at 8 o'clock your time. But everything on here is open source, and these notebooks are also already on the internet. So feel free to download things. You can run them later if you want. You can run, most of these should run on a Raspberry Pi or an other ARM Linux board, ARM powered Linux board that you have. So the Odroid one is one we use a lot. Raspberry Pis, obviously, I have a stack of them. And you can run these notebooks there. The issue is going to be building a lot of the required libraries on, like for the Raspberry Pi example, it takes a while to build OpenCV and it takes a while to build Armanin, which is why we set this up on an AWS instance. So you didn't spend hours and hours and hours waiting for these things to build. Any other questions? No other questions? We have time. If there are no questions, we can walk through this fire detection notebook, which has, let's see, it's got images of different fires. Whoops, wrong thing. And if you're running Jupyter Notebook and the cells have already been run, you can always click kernel, restart kernel, and clear all outputs. And this effectively resets it back to empty. So this is fire detection with ARMNN. This was done by Wei a few months ago. Thank you, Wei. Same thing as before. Make sure you do all the correct imports. You can load the image, define it right here. This is running 350. Print image. And then just like we did before with the COVID-19, create a parser, load the network, get the input binding info, create the runtime and choose the backend. You also are going to want to optimize the model for CPU. So that's choosing the backend and then optimizing the model. You load that network, create the output binding, get the output binding info and make an output tensor. So that way you can get the output. Skipping profiling this time, and then you run inference. And on this one, you should have an answer. What predicts fire? Wade, do you know if this model predicts things after fire? Like, is it predicting fire as well as the results of fire? Or is this just?
I think so.
Interesting. I'm going to try a different image. That's it.
Yeah,
that's a weird
there's
one.
a couple, like open country, the bottom two.
Okay, open country land. Okay, here.
Yeah.
Where'd my image go? Thanks, Wei. Let's see.
Okay.
And then, so if you change anything and you're not familiar with Jupyter Notebooks, just rerun that where you're importing it, and then you can just rerun the inference since we've already loaded the model. Okay, that also predicts fire. We're gonna have to look at this model. I don't think there's any fire there.
Okay, let me double check.
No, it's okay. It's just interesting.
As I migrate this from a Python script to the Jupyter Notebook while you guys were talking. I did it really fast.
Thanks, Ray. Yeah, I have found that sometimes quickly trying to take a Python script and importing it to Jupyter Notebook does not work very well for some reason here. We'll try this one, 355. Yeah, it predicts fire. Of course it does. Let's try this one. Okay. That's effectively it. Feel free to play around with these notebooks for the next hour or so. After that, I'm going to shut down the server. You can download things from the server right now. So feel free to do that, and you can run it later. You just need to have ARMNN installed, and the installation instructions are online. You can also wait a month, and then it's pip installable, which makes it slightly easier. So yeah, that's pretty much it. Any questions at all? Feel free to also just play around with Jupyter Lab. There's a lot of interesting things you can do. This is one I was working on and didn't quite get working. But basically Python libraries, and then there's a few specific things for Jupyter Hub and Lab from the IPython library. So for example, you can play video files in your Jupyter Notebook. Let's run this. The bounding box one is probably not going to work because I didn't install everything for everyone. But this example is online here, and you can run the script and basically do bounding boxes on either recorded video or streaming video. So, and this is another good PyArmNN example. All right, I think that's it. If no one has any questions, that's all I have for today. Play around with Armanin. Feel free to download these notebooks. Check out the GitHub. You can go to our ARM developer website, which also has more walkthroughs there. A lot of them around PyArmNN or ArmNN too. Okay, yeah, if that's it, thanks everyone for attending. Feel free to reach out anytime. And yeah, let me know any questions you have. Yeah. Hopefully you enjoyed it. Yeah, and learned a little bit about ArmNN, as well as good techniques for like running inference and deploying things on for Cortex-A devices.
Okay, so once again, thank you so much. Okay, so yeah, okay. So I think all the questions have been asked already through the chat or either the Q&A. Once again, thank you so much for this masterclass and for all you attendees at this time, even at the end of this day here in France. So once again, triple thanks to this amazing ARM team and Remy and Flora for the connection. I wish you all a very nice day wherever you are. And I sincerely hope that it has been useful for all of you. So once again, thank you to ARM team and to Telecom Valley for organizing this masterclass.